For our final project, we have made the solar tracker, presented by Team Helios Dial, created by
Edgar Granados
and Richard Castro Jr. So we decided to make a solar tracker that is controlled by a website on a Raspberry Pi that acts through a program that's downloaded onto a STM32 Nucleo board. This website will be able to give manual commands to the tracker. There will also be an automatic feature that will use light sensors on the tracker to send data back to the website in order to find the best position of light. The devices we will use are the STM32 Nucleo board, as well as a Raspberry Pi that will communicate to the Nucleo board using UART. Commands will then be received by two servos, one controlling the x-axis and one controlling the y-axis of the apparatus. We will also be using light-dependent resistors, or LDRs, that will sense the amount of light and have the tracker follow that light source. The original design was going to have a battery attached to the solar panel, which would then store energy into that battery. But due to time restrictions, we had to cut it from the final design. An LDR is a component that has a variable resistance that changes with the light intensity that falls upon it. This allows them to be used in light sensing circuits. We used them in our final project in order to sense the most amount of light in a given area. Our code will then read those values given by the resistors and then turn the tracker in the direction with the most light. We will use the Raspberry Pi 3 to code a website that would act as the central hub of the tracker and have two main functions, automatic and manual. In manual mode, the website will send commands to the tracker telling it to move either vertically or horizontally. In automatic mode, the program downloaded onto the Nucleo board will take over and the LDRs will send data to the website to be viewed in real time, and have the tracker move into the position with the most light.
In this part, we will be covering the second main part of our final project, and that was the STM32 Nucleo board. So in these slides, we will be going over all the main features that we utilized in our final project using this board. So essentially, we needed the Nucleo board to receive commands from the Raspberry Pi. So in order to do this, we utilized something called UART communication. So what is UART communication? UART stands for Universal Asynchronous Receiver/Transmitter. And the STM32 board gives us a variety of options that we can use when choosing UART communication. So if you look at this picture right here, all these yellow boxes are all optional pins that we can use to establish a UART communication with another device. So UART-TX usually refers to the pin that will be transmitting the data onto the other device, while UART-RX refers to the pin that will be receiving that data from the other device. So using the application STM32CubeMX, we could easily utilize UART by editing its parameters to use a specific baud rate and whatnot. We also had used ADC, which stands for Analog to Digital Converter, in our final project. So Analog to Digital Converter is a system that converts an analog signal, such as the sound picked up from a microphone, or in our case, the LDRs that detect light and voltage, and that converts it into a digital signal. So this is done by taking small discrete samples of the signal and then outputting its value. Usually the higher resolution a device has, the more accurate and higher amount of digital values it can produce. And finally, the final feature that we utilized in this project was PWM generation using the Nucleo board. So in order to control servos, you need to generate a signal, and based on how long or wide that signal is, the servo will turn a certain position. So most servos run at around 50 Hertz, meaning 20 millisecond periods. So in order to have the STM board control these servos, we needed to lower its frequency down to around 50 Hertz, but by default, the Nucleo board has its supported PWM pins running at around 8 megahertz. However, we can easily lower this frequency down to 50 Hertz by using prescalers and counter period parameters that we can set using the application we had previously discussed. So manual mode, LDRs readings are here changing. Now when I use the controls,
I'm gonna go up and then the tracker will go up. So now, right, left, down. Okay, and now automatic mode. I'm going to enable automatic mode, and it's now enabled, so now the tracker will find the most suitable position. I can also use my flashlight, and if you can see it move. Okay, and that is the solar tracker.